Good afternoon, everybody. Bonjour tout le monde. Thank you very much for joining us this afternoon for Cameron-Rastogi's public thesis defense. I'm Marilyn Anderson. Had the pleasure of supervising Parag's work over the last 4.5 years. And as you will see, it was a very rich experience for both of us. As most of you know, probably a public defense is the end of a long process, part of the PhD that follows usually a master's degree and follows in Parag's case a bachelor in civil engineering at Purdue University, followed by a master's also at Purdue University in civil engineering as well. He registered to and got accepted to the doctoral program in environmental and civil engineering at EPFL, he joined, where he joined LIPID, the Laboratory of Performance Integrated Design, or LIPID, 4.5 years ago, as I said. So a doctoral thesis has several steps as well. After being accepted, you have a candidacy exam, which he brilliantly passed in 2012, and happens after 1 year with a research plan and the assurance that you're going to stay exactly on those tracks and don't leave them. And then in the following 3.5 years, you complete your thesis work, which culminates in the thesis exam. So today is not an exam, this is a ceremony, a public ceremony. Parag is already Dr. Rastogi, sorry. And so this thesis exam happened just before the summer in a small group, and this is where we have a lot of tough questions and questioning really on the scientific aspects. And today, I hope there will be many questions as well, but of course there may be more open-ended and free. So we are very happy to have this ceremony to close a wonderful 4.5 years of work, and we look forward to your talk. All right, Dr.
Thank you. Okay, so this is the very long and pretentious title of my thesis. I will go through the thesis and break down the title just so to set up the context. Before I do that, I'd like to acknowledge where I did this work and how, and I just noticed it's cut off from the top, but that's okay. So I did this work at EPFL, of course, and as Marilyn mentioned, in LIPID. So my advisor is Marilyn. I'd like to thank my committee who were very, very helpful in making this happen, and the funders down here who never get mentioned, but without whom none of this would be possible. So thank you, Swiss government, I suppose. So the outline of my presentation goes like this. There are some dire warnings about the future. There's some simple math. There's some pretty terrible jokes. And then hopefully you will realize how this work is useful to somebody who's not me, just to get my PhD. Hopefully it's useful to somebody else. So as I said, let's talk about the title first. The word climate features very prominently in my thesis because I was interested in it. We wanted to work about it, and the climate is really important for buildings. And the climate is something everybody knows, or at least something everybody has an opinion on. I can't remember the number of times I've been asked to forecast the weather, and I say nobody can really do that. And in fact, most of my thesis was about why you shouldn't try to forecast the weather and why that will fail. So the point is that when you're building a high-performance, sustainable building, the climate is a major factor. The other one being, of course, what the building is for, who's going to use it. Sometimes other things get in the way, like the price of real estate, but I didn't consider those things. What does the climate look like? It's a spiral map of monthly temperatures from roughly the industrial onwards. This is borrowed from the US Geological Survey. And what this shows roughly is that more or less every year, the temperature, the mean temperature has been climbing, so going outwards in this case, and then it goes into the future using a business as usual scenario. So if we continue the way we are now, that's how the climate will end up, 5 degrees warmer than it was in the 1880s. This probably will not affect you on a day-to-day basis much, but it will affect our societies a lot. It will affect crop growth, it will affect water availability, and it will affect building. Because imagine you designed a building for a different climate, and then it actually has to perform and exist in a different climate. In a more conventional graph, it looks like this. So we are somewhere towards the left of that graph, and with business as usual, that's the red line. We're going to end up with a pretty high, about 4-degree change overall. If we manage to control our emissions and really have, this some technological miracles, we'll hit the blue line and barely avoid disaster in terms of climate. But this is not so useful for a building scientist, building physicist, or an architect. We cannot use this kind of data necessarily. So I set out with this problem statement, how to take this stuff and make it useful for my work. So what I was able to produce looks something like this. This is smooth, so it's averages over years, because if I plot the raw data, you can't really see anything. So this is smooth. What you see on the left, the blue line, is what has already happened. This is the previous weather. And what this is telling you, if you can see the jagged peaks up and down, but roughly it's going upwards. Then the red line represents the mean change we expect over the next century. And the gray lines represent the limits of our understanding, in some sense, the limits of what we expect could happen. And you can see that we're already actually coming up to the higher limit. So we were, the IPCC and their associate organizations, the Intergovernmental Panel on Climate Change, they were already a bit conservative with their forecasts. And we are already hitting the top part of that. Another scenario that I considered was when we peak our emissions in 2050, and what we end up with a slightly flatter line, which looks marginally better, but I don't know if that will actually happen. Before I continue, there's an important distinction to make between the weather and the climate. I will use both words, weather and climate. They don't mean the same thing. Effectively, weather is what you're experiencing right now. It's hot outside. The weather is what you experience at any given time in the future, but at an instant. And if you were able to record this over a long enough period, you would see patterns, and that's what we call climate. So it's very important to note that climate is a human definition. The Earth doesn't care about things like return periods or extreme events. The climate just is. It's only when humans are affected that we care about it. So as far as humans being affected goes, the second part of the main title is the sensitivity of buildings. That does not mean that the buildings start crying. It means that it's not the usual use of the word sensitivity, which implies the ability to sense things. Rather, in this case, we mean how the building reacts to the external stimuli, which in this case are temperature and humidity and solar radiation, the sun, basically the climate, the environment outside. And this happens through the exchange of heat and mass. And by mass, you could be air coming in and out, there could be some rain coming in, moisture coming in, and heat, we all understand because it's coming in right now, it's pretty warm. This is what we try to model when we do building simulation. And I'll introduce a little bit about what building simulation is later on, but that was the main method of research and work in my thesis and in the field that I'm trying to address. So when I say buildings, I mean really any buildings. It could be offices, it could be residences, it could be institutions, it could be mausoleums. No, I'm not that worried about modeling the Taj Mahal because it's not statistically representative of any kind of building. Nobody's going to spend the equivalent of your country's GDP to one building, right? So let's go to the which is involves the word future building energy consumption. The future is obvious. We're trying to forecast. We're not trying to forecast. We're trying to guess. We're trying to predict something. And as far as energy consumption goes, it doesn't just, when we talk about sustainable buildings, it's not just energy efficiency. It doesn't mean putting in a nice, better air conditioner or better heating system. We have to keep in mind that the building creates a certain indoor environment under certain outdoor conditions. And if you as a human being are willing to accept them, no matter how cold or warm or humid it gets, we don't need to use energy at all. And that's the most sustainable building there is. But we need a very narrow range of temperatures to survive as human beings. So that's why we use energy. So it's important to note that this energy consumption in buildings only happens because people use energy, not the buildings themselves. So we don't need to get locked into this idea of efficiency. We have to first think about why we use the energy in the first place. So in my case, in my thesis, a lot of the time that the building energy consumption was theoretical. It's about the gap that exists between what is and what a human being would like it to be based on certain assumptions. And of course, you're thinking human beings. Yeah, everybody has different preferences, but we can sort of approximate what we think your preferences would be, or we tell you what your preferences are, and then you follow them. So at the center of my thesis is this computer, which looks like a Mac. I actually use Windows most of the time. It's BPS, which stands for Building Performance Simulation, just to distinguish it from the fact that I'm not simulating the structure, for example, or earthquakes of that, which other people do in my department. I'm specifically talking about the simulation of heat and mass as it flows through the building. And how it flows is through the building envelope. So envelope is sometimes also called facade. In my thesis, I make the distinction: facade is what you see on the outside, and envelope is all the layers. So the walls, the windows, the roof, the floor, more or less. It's like the clothes of a building. As you can imagine, that's what mediates between the outside and the inside. So it's very, very important to be able to model things, the envelope, and what happens inside when the envelope changes. It's also called the building skin. That's a cooler word to use, perhaps. It's very calculate the building energy consumption, which is why I focused on it, of the many thousands of things that affect it. So we're back with our BPS, Building Performance Simulation, in the middle. You input things that are like design options. Now this is a very abstract representation of a house. So imagine you're making a house and you want to be able to choose what kind of roof goes onto it, what kind of walls there are, how many windows you want, because presumably you want people to be able to look outside. It's not sustainable to have windows, but you want people to be able to look outside. You don't want a bunker in the ground, because that, I think, in my opinion, would be a terrible house. But I call these design options because these are more or less under the control of the person making the house or designing the house. You can choose how high it is going to be, how thin it is going to be, how many windows it will have, how many porches it will have, that kind of stuff. And when you put it through this abstracted calculation, a simulation is a set of calculations done in the computer, you get something on the right hand side, which is basically on the y-axis, which is the vertical axis. You would have, let's say, energy use or comfort, number of hours you're comfortable, and on the x-axis you're comparing the horizontal, you're comparing different options. So presumably you want the most comfortable house with the least possible energy use. That is a basic assumption of my thesis, that you do want the most comfortable house and you want to use the least possible energy to achieve it. If that's not your goal, then that's a different conversation. And like I said, this energy use is very contingent on our current culture. And I have this quote which I really like: achieving thermal comfort predates by thousands of years the development of the theory of heat exchange. So just because we can quantify it now doesn't mean that people didn't think about thermal comfort in the past. It's just that now we have electricity, we have heat pumps, we have air conditioners, we have ways and means of controlling things we couldn't control before. There are even researchers that can track you as you move across a room and blast a beam of heat towards you, which I find a bit creepy, but that's one idea to control energy use. So there are two other things that go into this melange of algorithms and math. The weather, which is the focus of my thesis, which is why it's in bold, and occupancy, so which is human beings, human interaction, because we have to, the building has to exist for somebody, otherwise the building is of no interest to us, except aesthetically, of course. So what I in my thesis proposed, sorry, let me go back one slide. Let me explain the header of this slide. When we simulate buildings now for the future, remember we're trying to either design new buildings or we're looking at buildings that already exist. We assume that we have perfect knowledge of all of these inputs. So all the design options, we assume that I know exactly how this wall is, how this window behaves, how this roof is. And I also assume that I know perfectly how you will behave in a building and how the weather will be in the future. Now, if my tone didn't indicate it, what I'm trying to say is that this is not a tenable assumption because it leads to very, very, very wrong results. In the UK, they found, for example, that we could be off by 250% in any given year. Now, I don't know of any other profession that gets away with a 250 wrong prognosis. So, what I propose in my thesis is that we could have a slightly better way of doing this. A better way. I don't know how impactful it will be. We'll find out in the future. Which is what I call a stochastic paradigm. Stochastic is a big word to mean random. And why that would be more useful, which sounds kind of counterintuitive, is on the one end, I'm talking about having knowledge and controlling things. On the other end, I'm saying introduce randomness into your calculations. When I say randomness, I literally mean pick things out of a box kind of randomness. And so if you were to read my thesis, this would be clear why this is useful. I won't go much into the details of why that happens, but the two keywords to keep in mind are uncertainty analysis and sensitivity analysis. Uncertainty, as the name implies, is what we don't know. And when you have random simulation, it helps you to know what you don't know. Sensitivity analysis is know what affects the outcome from your simulation. So when you have a computer, a system in a computer, right? So remember, this is all happening abstractly. This is just a bunch of equations, right? For an equation, this much of wood with the same properties coming from a Douglas fir or from a pine is exactly the same thing. So we're not really talking about real objects. We're talking about abstractions of those real objects. In that sense, what you would get with random simulations is a new kind of graph that you see on the right. So it's again the same graph as before, where there were dots. So a single point estimate of the future. Now I have a box plot, so an estimate of the variability that can occur in the future. And as you can see, what I tried to indicate with the different heights of those boxes is to show that not all buildings, of course, react to the same conditions equally. You know, like I said, the weather just is. It depends on how your building reacts to it, and that's what's interesting for us. I want to know what's happening inside my building. So, for example, we are talking about sensitivity. A closely related concept is robustness. Robustness is the ability to handle changes. Changes usually which you did not predict. So, for example, in this case, B2, building 2, is more robust because in most cases I know exactly it falls within a very narrow range, the energy consumption level. And B1 and Bx, whatever n, can fall within a much wider range. This is very useful if you want to know more or less how much energy your building is going to consume in the future. For example, maybe you have a contract or you want to set a tariff with your electricity utility. So the reason I promised a lot of terrible jokes. So a joke that I like really about uncertainty analysis and how I try to justify it to practitioners is to say that a little knowledge may be a dangerous thing, but it is not one half so bad as a lot of ignorance. And right now, I think we are really going into the ignorance stream of things because nobody comes back and checks your calculations afterwards, because somebody builds the building, somebody else designs it, somebody else occupies it, and we don't know who owns it. So the person who's actually living through the building never comes back to you and says, this is not working how you designed. And that's how we assume things are going right now. So the point of my thesis is to change this process and inform people better about the future. So there are two parts to the thesis. The part one is a weather generator, which I found the best way to describe it is from one of my favorite comics. So the air changes every day. Every day clouds move around and the rain comes and goes and winds change. And every day people all over the world try to figure out what the air is doing and where the rain will go next. That's it. Literally what we're trying to do actually. We're trying to figure out how the clouds will move, where the rain will go, how the temperature will be. But like I said, even the best computers now cannot really do it to an exact level. So instead, we play around with random simulation. The parameters of interest, so the weather aspects of interest, are temperature, humidity, and solar radiation. Solar radiation means sunshine. This is what a schematic of my weather generator looks like. I will not go into the details except to tell you that this idea of bringing up weather, which is a time series effectively, into its frequency components is not solely my idea. It comes from literature from the 70s. I'm the first person to apply it in this context and for this usage. And if you want some details, we can talk about it later. And I'll just show you what those files look like. So these are 4 graphs, and I'll show you a movie in a second. So I'll explain before what these graphs are. On the top, you have a plot of temperature in the 2020 and 2080. So it's a guess, right? And each time it plots one line, that's a line, right, which is a very jagged line. What it represents is one possible scenario, future scenario for temperature in Geneva. This is all for Geneva. And on the bottom are 2 very useful kinds of graphs called, it's a probability distribution function and a cumulative distribution function. They're closely related. I can tell you the details later if you're really interested. But really what you should note is that the orange, which is 2080, is generally going to fall to the right of the blue, which is 2020, showing that it is slightly warmer. That's what we expect to see. And let's see if that actually shows up in the movie. As you can see, the plots in the top are individual years, estimate, guesses, and the bottom is the same thing being plotted like a summary. And usually, the oranges tend to be on the right-hand side in the bottom of the blues, which are on the left-hand side. What that's trying to say is something we sort of know already, which is that the 2080s will likely be warmer than 2020s. What that does not mean, though, is that you take the weather now, as it is, the record, and just shift it up by 1 degree everywhere, or 2 degrees, or 4 degrees. We don't know, so we have to generate it randomly, which is why I generated, for example, in this example, I generated 50 different variants that could happen. Now remember, all of those variants individually are wrong. It's together that they give you the right idea, and which is why it's important to have them all plotted together. So yeah, this is what the final result is. Give a few comments before moving on to the next part. What I'm trying to do is what-if analyses. So it's, as the name suggests, it's to see what would happen if something else would happen. So how would my building behave if the climate changes a certain way? I'm able to incorporate climate model outputs and the procedure generalizable, which, as we know, is very important for science. The ability to take my work from a context of EPFL in Geneva and use it anywhere else in the world. And this is really the first time we managed to demonstrate that, because previous studies have always been about one climate, using a lot of data from that climate. And now we're able to demonstrate that with just a little bit of data, we can do it for any climate we are interested in. The limitation, of course, is that depends on the quality of the source data, source weather data. Source file means source weather data. So if you start using, for example, for Geneva, you were to start using the weather data of Berlin, then you made a different mistake, and I cannot overcome that. You know, you're talking about Berlin, you're not talking about Geneva anymore. And I cannot generate heat waves on demand. That's a very small technicality, but that's something to improve in the future, because heat waves, as you can imagine, are of great interest to people who work in buildings. Right now, they're generated inefficiently, let's say. So the major issue, though, with this kind of approach is that it's computationally expensive, which means you need to do it many times to get the right answer, to get an answer that's useful. And that leads, this red box is trying to show you it's not good, right? Computational expense is not good. So we have something to replace it, which is a data-based emulator. And there are lots of warnings I will give throughout about emulators. The first one is if you torture the data enough, it will confess. You can make the data say whatever you want it to say. So this is a tricky terrain to enter, but nevertheless, we entered it, and we'll see what comes out. So is a regression model. It's an equation that represents other equations or other systems. It's just that this equation, the emulator, is simple and fast. That's the advantage, and it should have as much fidelity to the original system as possible. But of course, we'll lose something. It's also called a surrogate model or a meta model, and I don't know why there are 10 different names for it, but we do, and they're all in my thesis. What kind of regression? Well, when I looked at the books, I found this advice that all models are wrong, some though are better than others, and do not fall in love with one model to the exclusion of others. So that's the sort of the conclusion actually of my thesis as well, is that the model I propose is better. It's a family of models, but that doesn't mean it's better in every situation. Sometimes other models will work. So the objectives of this emulator, this regression model, this meta model, this surrogate, this equation, let's say, this simple equation, was to give probability, so probabilistic estimates. Remember, we're talking about random simulation, and randomness and probability are sort of the same idea. Probability is one way of quantifying randomness. It should be able to handle non-linear behavior, which is things that are aligned, and something that are non-linear is not aligned. That's a very abstract concept, so we'll have to go into details later. And it has to be customized to your problem, because current models, regression and meta models, are not customized to your design problem. They're customized, well, they're not customized at all. They rely on very large databases. So let me give you a quick example of a home simulated in Geneva. When I use my model, on the x-axis is prediction. Sorry, it's simulated, it's plotted the wrong way around. But okay, anyway, on the x-axis is what my model says something should be, and on the y-axis is what I calculated from a more expensive simulation. And what I'm able to show you, and if you have questions, I can go into the details later. This is, by the way, this is heating energy use, and these are z-scores, which is why it goes from -1 to 2. Of course, you cannot have negative energy use, which would make no sense. So it's a z-score. I can go into the details of what a z-score is later. It's just easier to work with in this kind of situation. What I was able to achieve is that with 0.3% of the data that I had at hand, I was able to make a model that represents the other 99.7% of the data, which is a huge savings in terms of time. And this could be a very useful thing when we're talking about doing random simulation and design. Again, I'll leave the details for now and go to the advantages. It gives them the mean and variance. Mean is average, the same as average. Variance means how quantity varies, based on certain conditions. The model is customized to the building that we're designing in the moment, and it's a very cheap substitute for initial estimation. Remember, 0.3% of the total data was able to explain the rest 99.7%. The limitation is that it's tough to follow the inner workings compared to the simplest models that were first proposed by Gauss and Legendre in the 1800s. It's the model that I'm using is significantly more complicated, so it's tough to follow what's going on inside, which is not great. And the results depend on how good your input data is. But that's not something you can change in any model. Garbage in, garbage out. Right? It is possible to retrain the model when you have more data, of course. And of course, another limitation to keep in mind is that sometimes the regression leads you where you don't know. So I'm sure people who do regression will understand this comment. If it's easier to find constellations in your data more than R squared, don't trust that R squared. And I found this to be particularly funny, which was with 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk. Unfortunately, I didn't arrive at the point where I could make this elephant wiggle its trunk, and I did try to use it using a Python script. But like I said, terribly nerdy jokes, but they're funny if you read my thesis, right? Yeah. So the conclusion, what is the point of all this? We have introduced a slightly more complicated but much more useful way of doing building simulation vis-a-vis weather. So that's what the extreme left, that black box represents. Lots of weather simulations, lots of random weather inputs, which gives you more informative outputs from your calculations. We have introduced an emulator, a regression model, a meta model, which makes this whole process faster and therefore more practical. What I have not done is check to see if, this is part of the future work, is to see if the source data itself is reliable, right? And if the simulation itself, so have you done the right calculations to train the model to begin with? Because if you train it with the wrong model, wrong data, then the model will be wrong, and I can't do anything about it yet. And more importantly, does having more information change the decision? And this was not in the scope of my PhD, because I'm not really an expert in decision theory and all those kind of things. But it's not always obvious that if you have more information, you'll make the correct decision, especially when we don't know what the correct decision is. Because we don't know what the ideal building is, we don't know what the best building is. We just have to sort of get there with some hits and misses. The outlook that I would like to leave you with before I go into more broad outlooks is that exact predictions are usually misleading. If somebody is giving you an exact prediction, it's probably wrong and it's not useful. And uncertainty, confidence, and risk. Risk is something we all understand. That's why I buy insurance. Are more informative than single point estimates. So it's not useful for me to know, well, it is kind of useful for me to know exactly the day I will die. But it's more useful to know that I can have some insurance so that my dependents are looked after when I'm gone. Think of it the same way. We have to calculate somewhat similar things for the building, insurance. So, zooming out, out of this details about regression models and everything. We've gone from a deterministic paradigm to a stochastic paradigm. Remember, going from single fixed point, fixed calculations to random calculation with random inputs, sorry. We have estimated that this kind of information will improve high performance design. And I'd like to clarify again, high performance design does not mean having a better air conditioner. It means providing a better building for the climate and for the people who are going to use it. For example, this building, which is a great building without air conditioning. We've discussed why this is important in the sense of climate change adaptation. We've gone from mitigation, where we're trying to reduce our emissions so the climate doesn't change, to adaptation, where we realize that the climate is changing, so we have to adapt to it. And this ability to calculate risk due to climate is a big part of being able to adapt to climate change. This just gives you an estimate of the bluer the country, the more they have done since 1995 to improve their adaptation to climate change. It looks like Europe and North America have not done anything. Actually, that's not the real picture. It's just between 95 and 2014, they haven't done much. But before that, they were already more prepared for climate change. You know, the best way to be prepared for climate change is to be rich. So you can imagine that the North America and Europe do pretty well on that score. But everybody else is improving, so that's good news. I'd like to leave you with these words from Khayyam, which is to say that, you know, if you do something now, the decisions you make now will affect people in the future, will affect yourself in the future. And when the moving finger writes and it moves on, you cannot cancel back the actions you make now, which is why I think this kind of work is really important. Because when you make a decision about a building today, well, most of you don't, but the architects and the engineers do, it's going to stay in place for 30, 50, maybe 100 years. Okay, depends which market you're in. In Japan, they break it down in 30 years, but in many other countries, they keep it for 50 to 100 years. And the next time you will have a chance to renovate or change, only then can you change that decision. So it's a huge decision to take for so many years based on conditions you don't really know. So using the style of simulation I proposed in my thesis, is a better way of making those same decisions. But at the end of the day, don't panic. We'll be fine. That's it. Thank you.
Thank you very much, Parag. The floor is open for questions from the audience.
Because Geneva Meteor Station is older, it has better data. Also, when there was a large American project to map weather data around the world and to make standard weather data for engineering calculations. And I don't know why, but Switzerland only volunteered Geneva. That's the only weather station that exists in that data set for Switzerland. And since I came from the States and I was using that data set, I was like, well, Geneva's close enough. So, yeah.
I have a question about resiliency. So if you do have synthetic future weather files and you are in the building industry, which areas are going to see the biggest impact on their future predictions? And is it more about like heating demand, cooling demand? I mean, do you have an answer to that? Like, who would be most interested in using your
You mean
files?
in terms of which geographical region?
Geographic region.
Yeah, so I've mostly looked at North America, India, and Europe. So I can only comment about that. In general, before I make that comment, this is kind of not very just, but how it's going to work out is that the people who did not contribute to climate change, so the poorest countries in the world, will be affected the most by it because the weather will change. They don't have the resources in the societies to adapt to them. What will happen is that it's not necessary that if you have a cold climate now, it will become slightly warmer in the future. You can expect more extremes, and that's what the models say right now. Of course, those models could be completely wrong. Based on what we know now, I would imagine one specific place, the Pacific Islands, because they will disappear. But when it comes to heating and cooling demands, or more peak demands, for example, I think most of the world actually.
Like a cooling climate more or a heating climate more?
Cooling climate more. Yeah. So that's the question. Yeah, because We need cooling demand, mostly in the morning, in the daytime, in the afternoon, and towards the evening. And places that are already hot now will get a lot hotter. So they will be affected much more. And remember, there's nothing to compensate on the cooling side in the winter. Because if you have a climate that's mixed between a hot summer and a cool winter, whatever extra energy you use because of a hotter summer, you gain back because of a warmer winter. But if you're already in a hot climate where your winter is nice and pleasant, like where I grew up, then when the winter becomes slightly warmer, it's of no advantage. Whereas when my summer gets warmer, it will be a lot worse. For if you want a real life demonstration of this, you can go to the Middle East now. And places that used to be orchards are just desert now, and so it's going to affect them quite badly. Yeah. Because we need cooling demand, mostly in the morning, the models I used in my thesis? Yeah, so they are existing buildings. And when I put air quotes around that, is because they come from a database from the US Department of Energy. They're meant to represent the average building of one particular type in North America. Why did I again use North America? Because they have the best data. So for example, I used the average large office, the average medium office. And then to get some variety, I used a home in Central Europe. Mostly because I was not particularly interested in going into the details of specific building. I just wanted an abstraction that is good enough. And so that database worked very well for me.
So are you able to compare for each time? Do you want to estimate energy consumption? And then you use simulation?
The models I use in my thesis? Yeah, so they are existing. And I put air quotes around that because they come from a database in the US Department of Energy. They're meant to represent the average building of one particular type in North America. Why did I again use North America? Because we have simulation. So for example, average large office. Right. So that's what we call calibration or post-occupancy evaluation. So once people start using a building, what happens, right? Can we compare it to our initial estimates? In my thesis, I don't do that because that's a whole different can of worms that I didn't want to open. But in my future work, actually, I'm going to look into that. What I will say is that nobody can ever predict the exact consumption of a building in the future at a given point of time, right? If you turn on the toaster, I cannot predict that. And the toaster uses a lot of energy, right? So instead of trying to predict when you're going to make a toast, what we do instead, and what I plan to do in the future, is use databases of similar buildings and try to extract features of measured data and try to compare it to what we get from simulations generally. So that you know when you're simulating that your building consumes 20 kilowatt hours per meter square, let's say, and per annum. And buildings of this type have been found to consume between 5 and 35, let's say. So you kind of know you're in the ballpark and you know you fall in the middle. Unfortunately, that's the best we can do because, as you know very well, each building is unique. Each person who uses the building is unique. So to make an exact prediction would be, well, almost impossible. What I will say is that nobody can ever predict the exact consumption in the future at a given point in time. If you turn on the toaster, I cannot predict. The toaster uses a lot of energy. So instead of trying to predict when you're going to make a toast, what we do instead, what I plan to do in the future, is use databases of similar buildings, try to extract features of measured data, try to compare it to what we get from simulation. Right. It depends where you are. Because if you're in the developing world, then most of the buildings that are going to exist 30 years from now have not been built yet. Whereas if you're in the developed world, so in Europe, North America, Japan, all these places, well, not Japan, Japan's an exception, you know that the buildings that exist now will likely exist 50 years from now. Now, they will get renovated, like you said. The concept of what is acceptable in a building changes over time. And so I was able to model so because this is an American database, the cutoffs are a bit strange for Europeans, but it's pre-1980, post-1980, and new construction. In future work, we'll go into more fine grain. A collaborator worked on Swiss buildings, for example, and we looked at, no, actually, I was part of that paper. We looked at every decade in this century, and we noticed there was a change in construction standards. So, no, not always. It's not always the case that what you assumed about from your existing building stock holds true for the future. But it does in this part of the world, especially in Switzerland where we don't break buildings so soon. So, most of the buildings that are going to exist 30 years from now have not been built. Whereas if you're in the developed world, so Europe, North America, Japan, right. So that's the co-author I was mentioning, and we just wrote had a paper which said that actually so we're looking at Swiss regulations, which are always focused on tightening the building, making it more insulated, making it tighter than the International Space Station. Really. And what we found was that this is not the best way to go if your climate is warming. Because what could happen is that the amount of overheating you get in the summer, so when your building is too hot, it's not too hot right now, it could get much worse. Imagine there are no fans, there's no air outside to cool us down. That could actually be a pretty bad outcome compared to the amount of energy you're saving in the winter, if the winter is very mild. But I can't put that into law because we don't have an estimate of the future weather. But yeah, that's something to be planned for. Is that it's not obvious that the way we've been thinking about designing buildings now is the way we should be thinking about designing the buildings for the future. Had a paper which said that actually looking at Swiss regulations, which are always focused on tightening the building, making it more insulated, making it tighter than the international building. What we found was that this is not the best way to go if your climate is warm. Because what would happen is that the amount of overheating you get in the summer, so when your building is too hot, it's not too hot right now to get much. Imagine there are no fans, no air outside. Well, that could actually be a pretty bad outcome compared to the amount of energy you're saving in the winter and the but right. So this question actually relates to two theses, mine and the master's thesis of Georgia. We worked together on, and we were trying to see if we could quantify this trade-off between being a robust building. So remember, robustness is being able to respond to many different scenarios, usage and weather, versus a building that you have optimized, so you have made perfectly tuned to a certain condition. The problem with optimization, which is a mathematical technique for finely tuning your building to certain conditions, is that you don't know if those conditions you're tuning for will actually occur in the future or not. And most likely actually they won't occur in the future because you're using data from the past. And the climate and usage are changing. So how this could affect optimization, for example, this work, is it would lead you to conclusions that are not as fixed as we currently get. So it would lead you to more robust buildings, yes. And if that is a priority, then you would end up choosing the more robust option. But yes, the decision is the design. The question actually relates to two theses, mine and
can you say something about the relative importance of the meteorological variables that are actually being a robust building? Is it the air temperature? Is it the solar radiation? Is it infrared radiation? Is it the latent heat of precipitation?
Right.
That has the most impact on these couple of properties?
I cannot make a blanket statement because if I could, then we wouldn't need building simulation. It really depends on the dominant feature of your climate, and it depends on the way you've constructed your building. So, for example, when we were both in Davos, we taught in Davos, and a colleague cold but also very sunny. So he had a lot of windows, but the rest of it was well insulated. So the temperature doesn't affect him much as solar radiation, the sunshine affects. So when the sun comes into the house, it really warms up the house. So in that case, the sunshine is the most important variable. That's not always the case. If you live in a more cloudy climate, then the temperature itself could be affected, or even the amount of wind you get. So if we had more wind now, we could be more comfortable, for example. So right now, the ability to exchange the air would be the most effective thing. Yeah.
I just have a question regarding
cannot make a blanket
I just want to know if what units can make their promise. It really depends on the promises. I consider you now as a specialist.
So that's outside my thesis, definitely. But yeah, but if you read the reports, what they found was that if each country actually meets their target, they will still not meet the overall global target, which was 2 degrees, and now we're aiming at 3.5 degrees. And so I whether we're like kidding ourselves or I think we're kidding ourselves really on a very grand scale. But you know what Khayyam said, right? If you make that decision once, you cannot go back to cancel it. So yeah, that's outside the scope of my thesis.
That's not always the case. If you live in a more cloudy climate, or even the amount of wind you get. If you had more wind now, right?
On my authority.
Yeah.
It's a very good presentation. Congratulations for that. Now, the science is of no use if it is confined to labs and results.
Yeah.
It's of use if it is of use to humanity as such.
Yeah.
And your thesis, there's a wide variety of weather and wide variety of resources, economic resources between different countries and even different parts of the same country.
Yeah.
So how is it going to be in countries or underdeveloped?
Right. So I'll give you 2 specific examples of how this could be useful in the context of, okay, let's say India, because that's the context both of us know, and I don't want to speak about other contexts. When we are building now, we're building for the next 50 years in a changing climate, under changing demands, and the very nature of our cities will change. And the way we calculate all of these things now, the air conditioning load of the future, the electric load of the future, the kind of building we should build of the future, we base it on past data and a pretty bad estimate of the future data. So what my work, and that's part of the reason I wanted to make it generalizable, is that when somebody sits down with a computer in India or in Africa and decides to design a building for the future, actually they need it to be much more robust than a building here in Switzerland. Because like we said, if you are already a hot country, it's going to get a lot hotter. But the only way to estimate how much hotter and how much it's going to affect your building is for weather. Well, only way so far. I'm not saying nobody will come up with a better way, somebody might. But this is one impact, is how to actually design a robust building for the future. And again, I'm not saying you have to put a nice air conditioner. I'm talking about the whole building. Another use that I could foresee, and I can't foresee all uses, of course, I hope not. That'd be very boring. Another use that I can foresee is the ability to calculate on the whole grid, actually, the whole usage grid of a region, how your buildings will have demand, what the demand from the buildings will be, and what the production from renewable energy would be. So solar panels, as you can imagine, respond to the same variables, more or less. Solar radiation and temperature as buildings. So we can use this also for solar panels to estimate the production of solar panels. So right now, when we make all these calculations into the future, we are not able to make a scientific estimate, a good estimate of the safety we should build into our systems. This goes some way to addressing that problem. How we can build actually safety into the systems, grids of the future. So that's part of the application I can see, also in a low resource environment.
And again, I'm not saying you have to.
This is very nice. Almost final.
Thank you very much for your clear presentation. Also for non-specialists as I understand very well your subject.
Thank you. Thank you.
So, congratulations.